Hi, I'm Ryan and I'm with Lab Group 3A. This is for the Shack Cube Interferometer Lab. I'm going to quickly run through our setup real fast. So we have a Heaney laser here. It's coming perpendicular to our Shack Cube. It's actually being collimated by a lens that's inside right here. It's collimated going through our microscope objective, and our microscope objective is focusing on a spatial filter which is mounted on flat side of our Shack Cube. Now inside the Shack Cube there is a beam splitter, and that beam is being split off this direction and this direction. The beam that's coming this direction is the beam that we're testing. It's coming to our reference mirror and being reflected back through our system, and you can't quite see it on the camera, but we have fringes here because we have our two interfering wavefronts that are coming to the same focus. And Garrett and Jordan are both going to talk about the more specific nature of why this happens.
Okay, so I'm going to start, I'm Garrett. I'm going to start by telling you about some of the problems that we ran into in the setup of this lab. It's very sensitive to misalignment, obviously, because it's an interferometer that relies on reflection. But also the benefit of that is that it's a direct interferometer, so you can directly compare wavefronts. You know, one fringe will equal one wave of error. But essentially some of the things that we did were this beam expander in front of the laser here, it wasn't putting collimated light out through the microscope, and it took us a long time to figure that out because it wasn't set. So we had to figure out a way to fix it there, but we got help. And then, another problem was the spatial filter was a little dirty behind the microscope objective, and also the laser on its stand was a little loose, so it's not entirely perpendicular to the rail that the mirror is on. So there's a compounding effect here, but with some work we were able to get some fringes. And so now I'll start talking about the physics of the interferometer. It's essentially a beam splitter cube with a modified face here that has curvature on it. This curvature acts as the reference wavefront. So light coming in here will be reflected by this beam splitting element, the S-polarized light will, and it'll leave through the beam splitter cube, but 4% of it, because it's a glass area interface, will be reflected by this curvature here, and that will provide the reference wavefront, and it'll be refocused somewhere close to this exit face of the interferometer. So the light that does make it through, about 90%, will be reflected by this mirror with curvature on it, and then be re-imaged back. Once we can get these 2 points to coincide, then interference can happen. And in order to do that, you need to adjust the tip tilt of the mirror and then the defocus to get these 2 points right on each other. And then then interference will take the following shapes depending on what you have. Pause. Oh, and just as a final note, I'd like to say that we need to use this linear polarizer in order to better match the intensities of the light. Since only 4% is getting reflected, and more like 90% you'll get from the mirror, it's hard to get fringe contrast, but if you use the polarizer to attenuate the mirror reflected light, then you can get much better fringe visibility.
Hey, I'm Jordan. I'm going to talk about the use of a reference lens as opposed to a mirror. So setup's the same. Coming through here, we have our reference wavefront coming through the Shack Cube here, and it's passing through, and it's reflecting off this back surface and coming back this way through our system, and then we see an interfering fringe pattern here. We couldn't really notice any fringes from tip and tilt, but what we did notice, because there is no tip and tilt, so we had to tap it and we couldn't still see anything, but what we did notice is that we did get a lot of fringes, some due to defocus, but for the most part due to spherical aberrations. You could tell because the fringe pattern was concentric circles, and there were a lot of them. And another reason why there was a lot is because we have a very thick element reflecting here, so this reference wavefront's coming through our system here, reflecting off this back surface, and the optical path length that it goes through this optical element right here is thicker than the mirror, so we expect to see more spherical aberration due to that, which will give us larger OPD and more visible concentric fringes on our image plane here. And those are the main observations from this portion of the lab. Also, one other thing to note before I go is that we do not need a polarizer anymore to attenuate the signal, because we only have 4% reflecting off this back surface, so that's going to give us a really good fringe contrast at the image plane. And that's